concept was to convince you, I'm sure I'm not been any success in that we can replace this Hamiltonian with the dipole interaction, which is something like Q d, where the dipole d is given by sigma e. I mean, what I claim, I only claim, is that in the long wavelength limit, this complicated structure can be replaced roughly by interaction carried out by a dipole coupled to the charge. I mean, we can retain only the zero component here, in spite of the fact that the photon is real, and so it has no zero component. But nevertheless, that's it is called a theorem. If you want just to have a reference, it is known as Rieger's theorem. Can be found in books of nuclear physics, electromagnetic interaction, and so on. And although it seems to be contradictory to say that the theorem claims that something is almost equal to, usually a theorem claims something is almost zero sometime, maybe only Tuesday or only Friday, the other day no. It is contradictory, but to be formal, this is a theorem in the sense that this substitution is correct up to terms of the order u. Or to plus order in the relative sense. I mean, this is a given order, is by itself for the order or Q. What remains is order square. In this sense, it is a theorem. It states not only that an approximation, but it specifies at which order, in which sense it is an approximation. Okay. This is just to give a name to something unknown. It remains unknown, however. Okay, what we have to do now, we consider a nucleus, a double closed shell nucleus, and we take Euler scheme. Here there is a bunch of levels occupying, and here there is a bunch of levels empty. And we consider all the excitation that bring one neutron from this level down and pushes it up to this level up, leaving, of course, a hole in the starting level. We can describe the states that at this point are particle hole states as E or E denotes the holes and the particles. Well, we have seen that at this point one has to diagonalize the Hamiltonian in this subspace, in the subspace of the particle Hall excitation. And thus I write this eigenstate in the form sigma m in some coefficients m e where mi and the unperturbed in the sense that there are shell model states. They are unperturbed in the sense that they are the eigenvalues of an object which is one particle Hamiltonian. I mean, kinetic energy plus a central potential. So each neutron feels the same external field plus its own kinetic energy. Okay, that's the generic wave function, and then I have to diagonalize it. The second difficult point to be very difficult to be accepted is the fact that the potential V can be written in this form. J lambda where is D the matrix element of the dipole. What we are doing, simply we take this potential, which is the residual interaction, not the true nuclear interaction, the residual interaction, and we expand it in multiples. I mean, it will be a sum of dipole plus quadrupole plus octupole and so on. And in practice, if we are interested only to low-level states, this is a reasonable approximation. With the advantage that this is something which is called a separable. I mean, maybe you have seen somewhere what is a separable integral equation. Yes or not? No. No, we don't. It's a very simple trick. It's the same trick we use here. We have already used it with the Savada Hamiltonian, but disguised. The idea is very simple. Take an integral equation. The integral equation will be something like say 0, 1, y. Where unknown is this function here. Okay, more or less this is hardly solved. It can be solved numerically. There are a lot of techniques to solve it numerically. Forget that. Consider a very simple case. Assume that k, x, y is written for b, x. This is called the separable kernel. And the trick now is extremely simple. Use this, write it in this way, it becomes x integral 1 y p y p y equal okay. Now Now, if we multiply this equation by v of x on both sides, here squared, here becomes x, and then we integrate over x, 0, 1, 0, 1. Well, this is a constant.